Hi guys, welcome to our channel Swipe to Learn. Today we'll be seeing about recursion, its declaration, its types, arguments, and many more programs on recursion. Recursion is a very important and fundamental concept in programming as recursion helps in writing easy code and maintaining the code efficiently. Let's see about it in detail. As you know, recursion involves a function calling itself directly or indirectly to solve a program. It breaks down into simpler and manageable parts. If you don't know about the function, see the previous video where we'll be discussing about the function and different types of functions like built-in functions, user-defined functions. I think we have discussed about four types of functions in the previous video: built-in, user-defined, lambda functions and recursion functions. So these are special types of functions where we call the function itself. So let's see about what is its structure. It's a base case and recursive case. So here is a function named recurse, and we will be having a series of codes where in the code itself we call the function itself. So a function calls the function within itself is called as recursion here. So the base case is the case where the recursion usually stops, whereas the recursive case means where it eventually leads to the base case. Like this is called as the recursive case and this is called as the base case. Initial call is done through the base case and the recursive case always calls the function itself. So let's see with the programming factorial. As you all know, factorial of 5, or let's say easy one, 3 factorial. It is the successive multiplication of numbers 3 into 2 into 1 up to 1, that is 6. So this is denoted by the symbol of exclamatory mark factorial. So if you see with this here code, if n equals to 1, return 1. Else, we're gonna use this logic n into factorial of n minus 1. So if you want to go with the general basic coding programming, for I in range of 1 to number, we can multiply with 1 into the number actually. Suppose 1 into I to the new number, right? So 1 into 2, 2 into 3. The output would be the same 6. So if you go with this factorial of 5, it is calling the recursively. See, as you can see here. So 5 into factorial of 4, because so factorial of 4 goes n becomes 4, n equals to 1. No, false. It's gonna return n into factorial of n minus 1. N minus 1 is 3, factorial of 3. So whenever you go with the result, this 2 into factorial of 1 result is the function call of factorial of 2. Whereas factorial 3 is 3 into factorial of 2. So it's gonna it puts the value into a stack, recursion stack, where each value is booked and repeatedly it calls and it takes the values. So this is how a recursive call would work. So we have two types of recursion: tail recursion and non-tail recursion. Tail recursion is something we call it, there is no repetitive work, where like we don't have any additional work on it. Suppose factorial of 5 returns factorial of 5 minus. This is the different logic of factorial, where it calls factorial of 4 and 5 into 1, 3 and 5 into 3. Each time it's going to multiply and it returns. Suppose, whereas if you see here, 1 into 1, 2 into 1, we are going to use the value and put into somewhere. Like if you see with the previous slide, here there are some operations, like for each and every call we need to multiply some n into something. So this call results in something. Look, we're gonna like this, a stack is plain where you use the previous scenario values. Whereas if you go here, tail recursion, where we go, it is the last operation, 2 minus 1, 1, 1 into 60 into 2, 120. Answer would be 120. We are not going to the previous recursion stack. So this is tail recursion. And if you go on using some operations, then that is called as non-tail. So this is the same factorial code where we can write in the multiple recursion calls. This is tail and this is not tail recursion. So why do we need really recursion? So when we go with a complex problem, we break it into chunks and we perform this, we write this code, and instead of writing each and every chunk, we use the recursion call. When you find the problem is complex and we can divide it into smaller instances, we use the concepts of recursion. Recursion makes code readable and easier to understand. Mostly we use the nested structures. For example, if you go with the directory traversals, where you go with the nested files, suppose C consists of users and users consist of your name consists of doc folders, everything you go with the specified path of nested. Instead of searching a file through a single name, suppose you have not sorted any of them and you have say 100 files. If you want to search a file, you have to go through each and every file. If you group them into several files, you just go switch over through the directories and find the file. This is how recursion is helpful. And the popular algorithms works on this strategies are merge sort, quicksort, binary search, etc. So, however, recursion is mostly used concepts. We also have the disadvantages, same as its advantages. We take a new layer of stack, so it increases the memory overhead. And if you go on deep recursion, like number of calls, even so, if you want to find the sum of natural numbers, you can just simply go with the for loop, or you can also write with recursion. For a simple programming concept of finding the sum of n numbers, a for loop concept is eventually fine instead of using a recursion. If you are going with a factorial or deep and recursion algorithms, then it is easy to use the recursion performance because it has number of function calls and it has to call the function, it has to get the value and return the result, and then it has to perform operations. So instead of carrying these 5 steps, it takes the performance issues because it takes some time to complete all this. And sometimes we also feel a stack overflow error when we extend our recursion depth, the stack limit. So these are all the disadvantages of using the recursion. So let's see with the programs how to do some of first n natural numbers, printing Fibonacci series, GCD. We can also do these all in the basic programming concepts, but let's see how to do it in the recursion concepts. Let's move on to Python. Okay, let me go and write how to print the sum of n natural numbers. Sum of n numbers, it takes the value of n. If n equals to 1, I am going to return the 1. If not, I am using the recursion call of returning the n number plus sum of n minus n minus 1. Okay, print sum of n of 5. Check with the output. See, if you go and see with the logic here, for each and every time n is 5 now. So 5 plus what is the next number we will be getting? 4, right? Sum of n minus 1. N minus 1 is 4. 4, it goes and check 4 equals to 1. No, it adds 4 plus and it calls sum of n minus 1, that is 3. If we go with 3, 3 plus sum of 2. If we go with sum of 2, 2 plus sum of 1. The sum of 1 gives 1, 2 plus 1, 3, 3 plus 3, 6, 6 plus 4, 10, 10 plus 5 is 15 will be the result. So instead of this, we can go with the basic logic also. In recursion, we are seeing how to use this number. Recursion is something where the function definition uses the function call itself. So now let's see how to print the Fibonacci series. As you all know, Fibonacci series is something where we have a consecutive series. The first digits are always 0 and 1. And to get the third digit, we add the previous 2 digits. 0 plus 1 is 1. To get the next digit, 1 plus 1 is 2. 2 plus 1, 3. 3 plus 2, 5. Like this Fibonacci series continue. Let's write the code to print the Fibonacci series using recursion. So let me name this as depth Fibonacci n, passing the parameter. If it is the first. Suppose if n equals to 1, like we have only one digit we have to print, then obviously the Fibonacci series would be 0, right? L if n equals to 2, the second digit always should be 1. So if from third onwards, we will be going with the previous terms, Fibonacci of n minus 1 plus Fibonacci of n minus 2 in a series. So let me print Fibonacci series, print of Fibonacci of n. Sorry, say n5. You got your output as 3. Let's check. 0, 1, 0 plus 1, 1, 2, 2 plus 1, 3. First term, second term, third term, fourth term, fifth term. So nth term in the Fibonacci series is 3. You got your output right. So let's check with the next program of finding the greatest common divisor. GCD concepts. GCD, it's a very simple tool and code where GCD stands for greatest common divisor. If you go with 15, you can write it as 5 into 3, 30, 5 into 3 into 2. So what are the common here? This is common, this is common. GCD, greatest common divisor of the two numbers would be 5 into 3, that is 15. This is how you calculate the manually. So how I calculate is, let me take the greater number, 30. I'll divide it with 15, 2, right? Until I get 0, I divide it, and if it is true, then the number would be the GCD, like the result. So let's write the code. Def GCD of A comma B, B equals to 0, return A, else return GCD of B comma A mod B. Print GCD of 30 comma 15. Run this. You got your output. Say 30 comma 45. This is also 15, right? So this is how we write. Now let's see the next program, that is count digits in a number, like how many number of digits in a number and finding the power of a number. Suppose the number is 148. So 148, how many digits are there in this number? We have 3 digits. We know how to get the last digit by performing the modulus operation with 10 or dividing the complete with the floor. So let's write the code. Def count digits of n, count value is 0. Suppose if n equals to 0, return 0, else return 1 plus count of n floor division 10. Print of count of 143. Run this. See, you got your output as 3. What if it is 1435? It's a very simple, as you see. Now, let's go and find the power of a number. Suppose the base is 2. Suppose 5 cube. Base is 5. Exponent is 3. Base and exponent. So, we need to find, multiply the base. How many times? Exponent number of times. It can be 6 power 5 or 7 power 8, anything. So let's see how we write in the coding format. Define the function name power where the parameters are base and exponent, and then if exponent is equals to 0, okay, sorry, if exponent equals to 0, anything power to the 0 is always results 1, so return 1, else then return base into, again repeat the function power of, like already we have multiplied one time, so next we have to multiply n minus 1 of times. Suppose the number is 3, we multiplied number into, we have to multiply it to 3 times, so 3 into, now how many times you have to multiply it? 3 in 2 times, and that is n minus 1 times. So here that is the logic here, base into power of same base, comma, now I am making exponent minus 1. Okay, let me put comma here. Okay, let's find print of base is power of function of base is 2 whereas power is 3. Check with the output, you got your output as 8, whereas if the exponent is 1 and the number would be some 26786, even then the output should be, we have to get the output as 1. Same, if the exponent is 0, then you'll be getting whatever the value it as 1. So if we go with the check with the base of 5 and the power is of 10, that is 5 power 10, within fraction of seconds you get the output, right? So this is how we use the logic of using the recursion concepts. You're done with the programs. You can start using the recursion concepts for the basic high-end programs. So congratulations on mastering recursion. So it helps the function to look elegant and efficient. It has a well-structured flow. So, if you like this video, please do like, share, and subscribe and share it to your friends. Thank you, guys. Up next, we'll be seeing about the pseudocodes. Like, however, concepts you have seen about function and recursion, we'll be seeing the most important placements topic, pseudocodes, where we will be solving the programs and getting the result output.